In my video on Thursday, I interviewed Dr Alexandra Amon from Stanford University, who's part of the Dark Energy Survey collaboration. Now, just last week, the Dark Energy Survey put out 3 years worth of data. It was over 226 million galaxies that had been catalogued and mapped out to give us the distribution of matter and dark matter in the universe. And I interviewed Alex just to find out her role in the collaboration, working out how clumpy or smooth dark matter was distributed. And in that video, I really only left in about 5 minutes or so of our conversation, when really we spoke for a lot longer than that. So here is my full conversation with Dr. Alexandra Amon. So Alex, thank you so much for being here. Why don't you start us off by telling us, what do you do in the Dark Energy Survey? What have you done as part of this big 3-year data release as well? Tell us about this paper that you've written.
Yeah, I'm excited to be here and to tell you about this project that we have been busy working on for a number of years. So I work as part of the Dark Energy Survey, which is a large international team. It really is an enormous effort of mostly young scientists. And my role was in leading this cosmic share paper, which is the measurement of weak lensing due to the large scale structure of the universe. So this is particularly exciting because we have a data set that is unprecedented. So just in the last 10 years, these cosmic share or weak lensing data sets have really grown in the amount of data and the amount of power that they have. And so we've gone from just having thousands or tens of thousands of galaxies to now having 100 million galaxies that we use in our analysis for the Dark Energy Survey year 3 work. And that's exciting, but it's also very challenging because now we have so much more power. We have to be way more careful that we do our measurements accurately. And weak lensing is extremely powerful for cosmology, but it is a very challenging measurement. And that's because we're measuring the shapes of these very far away galaxies. And you're probably imagining a very beautiful spiral image, and well, we just draw a circle and measure a shape around it. But what we're really working with are these fuzzy blobs in our images. They're far away, they're a few pixels, some of them are sitting on top of each other, and we need percent level or precision measurements of the shapes of these galaxies, which is extremely challenging.
Yeah, they're such tiny fluctuations, aren't they? Like so small. And then you've got this huge data set. I'm sure people are wondering how you cope with so much data, right?
So for weak lensing, you need a large sample because, as you said, the measurements are so small that you wouldn't see the lensing effect on one galaxy. You wouldn't be able to tell the difference with your eye. But when we look at a sample on a statistical level, when we have 100 million galaxies, then we start to see these trends and these alignments and changes in shapes form some kind of pattern on the sky. And it's not just the shapes that we need, we also need the distances to these galaxies. And measuring the distances is as challenging as measuring the shapes. So we use the fact that galaxies further away might have different colors depending on their distance to infer the distances of our sample of galaxies. And both of these measurements are extremely challenging. And so it feels very rewarding that we've managed to get these results out from this huge data set that we believe are robust and that we've shown to be robust.
Yeah, I mean, I'm in awe because, I think I have it easy in comparison because I work with very nearby things and I get, what is called a spectra of a galaxy, right? Where you can get this distance from this redshift really easily because you can see, oh, here's this big feature of hydrogen that I know is at this wavelength, but it's been shifted to this wavelength. But you're working with images alone to work out redshift, right? Like that must be.
You have what we wish we had. So we only have photometric information. So we have images of our galaxies in a few different filters or bands, and then we can measure their colors, the differences between 2 bands. And that was actually work that was partly led at Stanford by a student that I co-advised, Justin Miles, where he led the entire analysis that we can't accurately tell you the distance to one galaxy, but we measure the distribution of distances for our sample. And that distribution we need to know extremely accurately. And that was part of the work that I was really heavily involved in.
I mean, it just still amazes me that you not only have you got this huge data set to deal with, But there's then also like 400 plus people in the collaboration that are all having to work together to do this and check that no wires have been crossed and that, everyone's got their own little niche bit that they're doing. Like organizing that, it must be incredible. Like you must be so proud to be just like one little cog that's part of that sort of giant machine.
Yeah, it is a machine. It's enough people that it's like a small village or country, and that's what's most exciting to me about in the Dark Energy Survey, that we have this enormous team. The range of expertise is for any of these weak lensing experiments or any weak lensing team. You need to understand. I started cosmology wanting to learn about cosmology parameters and what is dark energy, but you need to understand how the detectors work and why the telescope is messing up all of my images. And so the range of expertise and getting people to work together and to meet, let their expertise meet and connect the dots between this very complex puzzle is what was most impressive to me in the Dark Energy Survey, and the fact that in each of these components of our analysis, whether it's measuring the effects of the atmosphere and correcting for it, or our theoretical framework or our simulations, in every aspect, I think we pushed the boundary on what the field was doing and developed new methods that will help the field and help these future experiments going forward, and that was really most exciting to me.
So why is this measurement of shear so important? There's so many things that have to come together for you to do it. What can it tell us that's so important for our understanding of the universe?
Yeah, that's a great question, because we have so many different cosmological probes that tell us different information. So what does weak lensing bring to the table that we don't already have? So we have exquisite measurements from the cosmic microwave background made by the Planck team, for example, but they are probing a very different universe. They are making measurements of our universe when it's just this soup of particles, rather than what we're measuring with weak lensing, which is our late time universe, or the universe that we're more familiar with, where you have galaxies and stars and clusters. So really these two measurements together, these two types of measurements from the early universe and the late universe is what's most powerful, because when we compare their results, we're testing our standard model over cosmic time. So we're seeing if our one model that we've come up with works for 13.8 billion years of expansion of the universe. So it's the most beautiful and the most elegant test that we can create by comparing our measurements to the early universe. Weak lensing in particular is directly sensitive to the mass distribution in our universe. So it tells us where the dark matter and normal matter are in the universe. And by having these redshifts, these distances, it also tells us how this matter evolved over time, which is allowing us to get at dark energy. So it really is unique at being able to look at both aspects of our dark universe.
Yeah, it's like peering into the 95%, right? It's really fun.
Exactly, that's such a good phrase.
So, I mean, this paper, I think, got quite a lot of hype, or at least the whole 3 years worth of data dump that happened last week got a huge amount of hype in the media. And one thing they picked up on was these cosmic shear measurements showing that dark matter was smoother. Obviously, in the paper, you're very clear that, like, there's no statistical difference between this measurement and the previous measurement. So no statistically significant difference. Like it's like 2.1 sigma or something. How sort of excited or reined in should we be, do you think, about the fact that the measurement that came from DES was different to previous measurements?
Yeah, that really is the question. Is this exciting, or is this level of tension exciting? I think I will say the word unfortunately, that with the Dark Energy Survey, this was the data set that could tell us, we have unprecedented power, but our measurements kind of fit exactly in a way that it is low compared to what Planck predicts, or it is a smoother universe. And this is still exciting. So when I started my PhD, I was working with Catherine Hamans, who led the first kind of groundbreaking experiments from CFHT lens, where she found this smoother universe. And it is, without a doubt, intriguing that all of our measurements from weak lensing have shown a similar effect. Each of them on their own, like if we just consider the Dark Energy Survey year 3 results on its own, we have intricate methods of assessing whether these data sets are consistent or not, and we come up as consistent. But it is still true that our measurement is low, which carries on a trend that we've seen in all our measurements. So it's kind of annoying and tantalizing at the same time. We see something there, we haven't been able to answer for sure. Is it totally bang on what the early universe gets, or is it way off? You know, we're still sitting in that middle ground that is difficult to understand from DS on its own. What will be most interesting is being able to work with the other surveys to combine all our data sets and do a joint analysis of all three. And I think we'll really have the power there to see it, you know, to make more of a concrete statement about this tension.
But it's not the only tension, is it, right? Like there's the tension with the Hubble constant as well, with the same thing. Like local measurements get a different answer to what the cosmic microwave background predicts with our model. Like, is this just more evidence on the pile of there's probably something wrong with like the cosmic microwave background prediction? Like not necessarily the cosmic microwave background measurements, but like the prediction we then make.
Yeah, certainly. I think we're all trained as scientists to work with all the information we have. So it's whether we're going to think about what our analysis showed, which is unfortunately, in my opinion, consistent, but on the edge. But we know that there are other things cropping up, and that's certainly makes us keep doing our experiments. But it is hard to say right now. Are we connecting the dots because we want to connect the dots between these strange things, or do they each have their problems and they're all going to be fine in the end? It's extremely hard to say. But you know, on the weak lensing side, it just doesn't really make sense that all of our experiments are coming up on the same side or the same smoothness or lower value of this S8 parameter than what the early universe dictates. That is just, it is strange.
Do you think when the 6 years worth of the DES data dump comes, like in, I don't know when that might be, you probably can't tell me, but whenever that does come in the next couple of years, and that's going to be the full data set, do you think that will tell us or allow us to figure that out? Or I guess you've got your fingers crossed that is what's going to happen?
Yeah, so we have that data in the can already, and we've already started making our catalogs and doing the analysis. There's no time wasted. It is interesting because we're doubling our data sets, and it is challenging because unlike the jump from year 1 to year 3, we're not growing in area on the sky, but growing in depth. So the year 6 survey is twice as deep. The images are twice as deep.
So you'll get more distant things.
Yeah, and that is extremely powerful. So it's letting us look at galaxies further away, so we can see that evolution of structure more. But for the measurements that I was talking about, these measurements of shapes and measurements of redshifts, it makes our job a lot harder. So all of our methods will be pushed to the limit to be able to analyze this deep data.
I don't envy you at all.
This jump to deeper data is directly in line with what we're really looking forward to in the future. You know, DES Year 6 will be groundbreaking, but beyond that, we're looking at Rubin Observatory and Euclid. And these are all sky surveys that are very deep. So it is good practice. It is good that we have this stepping stone of DES Year 6 to learn to work with this deeper data.
I wonder whether this is quite a cruel question to ask of a cosmologist, but like, what's your intuition for like the tension between like local measurements and CMB measurements? Like if you were a gambling lady, like I'm a gambling lady, like if you were a gambling lady, would you, like, what would you put your money on?
I think it's strange that we all the measurements are showing this thing. What is kind of throwing in the DES results is that, you know, every time we add a little bit more data, we have shifted towards the measurements, towards the agreements with measurements from the early universe. So we are shifting in that direction, but with smaller error bars. So we're kind of holding the same position formally, but we are inching up. And so that kind of throws my hopes and my wish that we would be finding something quite glaring. What I think is most interesting is that we do our analysis blindly. So, you know, of these big cosmology experiments, and it's been done in weak lensing surveys before, but I think the dark energy survey, we really took it to a new level. We did not know anything about our data sets before we were totally finished. So we had 3 levels of hiding the truth about our data. We muddle our catalogs so that even if you try to make the measurements and do the analysis on your own, you can't. And then every analysis choice we make, every time we want to know if our measurements are consistent with each other, so internally consistent, we weren't privy to any of that information. So it really was this big reveal on the same day as the US elections, I should add.
Oh,
It's a very stressful
why?
day.
Who picked that day?
I have no idea why.
Did it take 5 days for you to finally get an answer?
We see the answer, the preliminary answers, and then we do have to run final chains. It was a situation where you had like the polling results on one page and the test results on the other page, watching them come in. It was a very anxiety.
I hope everyone took a holiday after that, like vacation for everybody.
But it's incredible to me that we still get somewhere even near to the early universe measurements, first of all, because what we're doing is crazy. We're measuring the shape of 100 million galaxies, shapes of blobs. We shouldn't really even call them galaxies.
I wouldn't.
It's nuts that we get even near the answer. It's certainly intriguing that we get very similar or totally consistent with other lensing experiments. I'm looking forward to the field, to all experiments in the field having this level of blinding, because it really makes you be very conservative and very sure about the choices you're making.
What do you think are going to be the big things that change our understanding of cosmology in the next 10 years? Or maybe even just confirm that, no, we had it right. What's going to be those things, do you think, that are coming up? Like, what should people look forward to?
That's a good question. We talked about Desier 3, and of course, that's just a couple years time scale. It is the future, but it's very near future. Even Rubin Observatory after that, it is coming online just the year after that. So we're thinking further ahead. And what I'm most excited about is seeing all the different fields merge. So we're already at a stage in our Desier 3 results. For example, in my paper, we do a little analysis at the end, trying to figure out what's limiting our measurements. Do we just need more data? Do we need to understand different modeling aspects? Or are we not calibrating our redshifts, our distances well enough? And what we find is that we're theory limited. So we are limited by our uncertainty in modeling essentially galaxy formation. And that's exciting because galaxy formation on its own is exciting, but also because, we really need our fields to start merging. We need to, for lensing, we need to be able to understand baryonic effects, and feedback processes. And we need to be able to understand intrinsic alignment. So how much galaxy shapes are correlated just because galaxies live in the same area of the sky. Not due to weak lensing. And as I said, galaxy formation on its own is interesting, but how interesting will it be when we all need to understand each other's research well enough to work together? So combining CMB measurements with weak lensing measurements and combining galaxy formation expertise with cosmology. That's a different level of expertise that I don't really know if any of us are prepared for.
I know, even bigger collaborations as well, right? Because you just named 2 things that I've written papers on, right? The shapes of galaxies in different environments, in clusters or in filaments or in voids, and then feedback processes from AGN, from like black holes that are actively growing. Like, that's what I work on. And I care about those things because I care about those things and I want to know those answers, but you never really think about how it then fits into so many other areas of work that you didn't think it would fit into. Like, the idea that my work could then eventually help you figure out like weak lensing is kind of strange to think, because that's not why I'm doing it, but that would be awesome.
Yeah, it is awesome. But particularly for me, I started in this field on the very observational side. So learning how to best make these measurements of shapes and redshifts. And in that frame of thinking, especially if you have 100 million galaxies, they aren't galaxies. They're kind of just a number, and you're measuring things from them. And now when we talk about combining like your expertise and my expertise, you have to think of them as galaxies, and you have to understand how they work. Otherwise, you won't really be able to use your data. So,
and that is a scary thought. Lots and lots of data sat there unused. I think that's the scientist's worst nightmare, right? Like, again, thank you so much to Alex for finding the time to talk to me for this channel. I know that she's mid-move at the minute from the US back to the UK, so it's a very stressful time for her. If you want to hear more from Alex, don't forget that you can follow her on Twitter. It's at AstroAlexAmon, or you can follow her on Instagram as well. Again, it's at AstroAlexAmon.